I'm a real fan. There are some people who, there are definitely people out there who write papers I read. There are some people whose papers I read 2 or 3 times, and Rina is that example. She's been working on hard problems and really going after contributions that are fundamental and non-trivial and just worth reading. So I got to know her, I think originally you were working on graphical models, if I remember right. So she was a PhD at the University of Chicago, and then moved to Stanford to do a postdoc and started becoming more interested in uncertainty issues and false discovery rate issues and multiple testing issues and so on. So she has done really beautiful work there. I particularly like the jackknife plus. It's one of my favorite ideas. And then the knockoff work she did was also really, really striking. So all just cool ideas. When you hear them, you say, damn, I wish I would have thought of that. So I don't have any idea what this talk is about, and I can't wait to hear. So let's welcome Rina Foygel Barber.
Thank you so much. Thanks so much for the kind introduction and for the invitation. I'm just thrilled to be here, and it's really great to be able to talk to so many people today and get to hear all the exciting things you guys are working on. Today, I'm going to be talking about actually 2 different pieces of work on a related problem, which is the problem of stability that I'll explain in a minute. And I've been super lucky to get to work with great collaborators. The first part of this work is joint with Byul Kim. She was my PhD advisee at Chicago, and she's now a postdoc at University of Washington. And the second part of the work is joint with Jake Soloff, who's a postdoc working with myself and my colleague Rebecca Willett. So this work is all about stability, but it's looking at it from 2 completely different perspectives. The first part of the talk is going to be a hardness result telling us why understanding stability is difficult to do. The second part of the talk is going to be a positive result telling us that actually something that we've been doing all along, bagging, actually has really nice stability properties. Okay, so please feel free to jump in anytime with questions. A lot of this is very new. The first part I've talked about like 1 or 2 times, and the second part is very new work, so your feedback is very, very welcome, and please feel free to jump in anytime. Okay. So here's the setup. So let me just introduce what we're asking about when we ask about algorithmic stability. So we're thinking of an algorithm as an arbitrary map that inputs training data and outputs some kind of fitted model. So the fitted model being something like a regression function that predicts y from x. And throughout this talk, we're going to be talking about algorithms in a black box setting, meaning that I feed in the data, the algorithm does things I don't understand, and then some model comes out. And I'd like to understand what properties that algorithm has without necessarily knowing what it's doing. So why are we asking the question in that regard? Well, making assumptions about what algorithms do is a restrictive setting in the same way that making assumptions about how data behaves can be restrictive. The more we can remove assumptions, the more we have methods that are broadly applicable, robust to all sorts of different situations that come up in modern data analysis. So in terms of thinking about our assumptions, we can think of this kind of hierarchy of questions we might ask and goals we might place on our methods. So if we're in an assumption-heavy setting, so like most classically, I might have like a parametric model and some kind of extremely specific algorithm to try to fit that model, so like least squares or something like that. Can my fitted model estimate the true conditional distribution of y given x? And so we can have these beautiful, strong results that characterize exactly how that happens and how fast that happens. In these assumption-heavy settings. But as we try to peel away assumptions and become more robust and more non-parametric, we maybe start moving down this list. So for instance, we could ask, okay, like I don't even believe that the parametric model is necessarily the true model for y given x, but can I nonetheless make some weaker assumptions that are sufficient to tell me that my algorithm is fitting something that has low risk? So something like, you know, the model class I'm working in is close enough to reality, things along those lines. But maybe I can't necessarily do that, but at least is it true that when I train my function, I have generalization, which in one version of what that means that my training error, like how well did my fitted model do on the training set, actually indicates to me how the quality of that model and how it will perform on test data. So this is asking much less. This isn't saying I want a model that's going to perform optimally well or nearly optimally well. It's just saying I want a model whose performance is going to continue at that same quality, whether it's good or bad, in future. But this is still asking a lot, because we know overfitting is real, right? Overfitting means that we might have training error be very different from test error. We might need to have methods that try to avoid that issue, things like cross-validation to tell us how good the model really is. So maybe in the most weak sense, we can ask ourselves, can I at least tell you, using some other technique, like a cross-validation method, can I at least tell you how well my model will do in future? So my model has a certain like future performance measure, some kind of risk. Can I use the training data in some perhaps more sophisticated way, like cross-validation, to tell you how well my fitted model is going to do in future? And by the time we get to the bottom, we kind of think of this as distribution free. Like, if the data is not coming from any nice distribution, maybe my fitted model is terrible, and I'm just going to say, okay, like this is this really high risk that this model is going to have in future. But even answering this last question, if data is scarce and I'm not willing to lose half my data to a holdout set, is not necessarily a trivial thing to do. And as we move down this list where we try to remove as many assumptions as we can, a lot of times in the literature, the last assumption standing is assumption that's along the lines of algorithmic stability. So let's talk about what that looks like. So in a strong assumption setting where we're parametric or something like that, or we're heavily regularizing the fitted model, then we might expect some kind of concentration or consistency that if I were to resample the entire data set and rerun the exact same algorithm, I would get similar answers. And this doesn't necessarily mean that my data comes from a nice distribution. It could just be that my data comes from any distribution, but my algorithm is some extremely simple thing that just concentrates really well around whatever its expected value is. But this is not what we often see in practice. In practice, even in nice settings, for example, we simulate sparse linear model data and we run the lasso. You run it and you change the data and the answer actually changes substantially. Like what's the support of the lasso, for example, can change a lot as you resample the data from the exact same distribution, even when the model was correct. And so we might think something weaker is happening, which is, well, I can't resample the entire data, but maybe I could resample a small fraction of the data, and with high probability, the fitted model would not jump around too much when I do that. And it's this last sort of weakest goal that's what we mean when we talk about algorithmic stability. So there's quite a few definitions of algorithmic stability in the literature. In the interest of time, I'm not going to try to survey them. I've just pulled out the one that's most relevant to the way in which we are analyzing the problem, but this is just one of many. So here's the way this definition works. I'm going to take data that's IID from a distribution. I'm going to take the same data set with 1 point removed. So just for notational convenience, I've removed the last point. But since the data is IID, there's nothing special about the last point. So you should really think of this as a training sample and the same training sample with 1 point removed at random. Then I'm going to run my algorithm and fit the model on both the full thing and the data set with 1 point missing. And then I'm going to take a new test point, xn plus 1, so out of sample, not one of the x's I trained on. And I'm going to plug it in and see whether I get similar predictions. And so algorithmic stability here requires that your predictions are similar except for delta fraction of the time. So epsilon parameterizes how similar they are, delta parameterizes how often that can fail. I want to point out that this definition is not about an algorithm. It's a definition about an algorithm with respect to how it behaves on a particular distribution at a particular sample size. So this is actually a property of the triple, the algorithm A, the distribution P, which I cannot see, and the sample size. So this is sort of a more statistically flavored distribution. It's not saying the algorithm has to do this on an adversarially chosen data set, just an IID data set. Now what we might want to know is, okay, given data that's coming to me from some unknown distribution, and given an algorithm that I have chosen, do those things together satisfy stability at some particular sample size n? So that's the problem we'll be focusing on for part of this talk. Okay, just a few notes. I'm writing this as though the algorithm's deterministic, but the framework can easily be extended to randomized algorithms, so things that use some form of randomization like stochastic gradient descent. I'm also only considering the symmetric case where the algorithm does not care in what order you feed it the training data. Again, this in the randomized setting where like SGD does care, but on average it doesn't care because it randomly shuffles the data. This can be handled in the framework, but I won't write that down to not have too messy notation. Okay, So backing up to like our hierarchy of goals, why do we care about stability? It's because stability on its own, without heavy assumptions on the distribution of the data, has a lot of downstream applications. So for example, generalization, learnability, like can you drive risk down as you learn from data coming from a distribution, and predictive inference. So let me dive into some of these just for some context and background for a few minutes before we talk about the results that we worked on. Okay, so for generalization, what do we want to do? So generalization, sometimes we think of it as meaning like, is the training performance on my training set indicative of the test performance I will have in future? But more broadly, we can think of generalization as, can I use the training set to estimate how well my test performance will do? And so if I have overfitting, the training error is not a good estimate, but you can use the leave one out estimate of my future error. So how well do the leave one out fitted models perform in sample? Does that represent how well the fitted model on the entire training set will perform out of sample? And again, I'm not considering more complex issues like distribution shift between training time and test time. This is just for IID data right now. And so results by Bousquet and Alassif show us that under certain conditions, if you have this stability condition, then the actual risk of the fitted model is very close to the leave one out estimate that you estimated in the training sample for that same fitted model. And the stability condition looks really similar to what we had. It says you fit the model on the full data set, you fit the model with 1 point left out, and now instead of asking are the predictions close together, this version of stability just asks are the losses incurred by those predictions close together. So what this tells us is that stability is sufficient, no distributions on the data distribution here, stability is sufficient to tell us that we can estimate the future loss of the fitted model. Switching to predictive inference, if we look at the goal of predictive inference, we have a new test point x, and I'd like to give a prediction interval around my y hat, my predicted value of y, that's going to contain the true response value y some fraction of the time, like 90% of the time. And a method has distribution-free predictive validity if for any distribution p that the data might be coming from, this holds. So here we can think about methods along the lines of conformal prediction, but more classically, something like jackknife or leave one out cross-validation could also be used to construct these intervals. So this is like, okay, I have my y hat. How big do I need to make my margin of error around y hat? Well, let me look at cross-validation or at jackknife, which is another word for leave one out cross-validation, to tell me how large are the errors that this model tends to make in the leave one out version on the training sample. And then let me use the empirical distribution of that to say how large will residuals probably be in the future, and that's how wide I should make my prediction interval. Okay, so here's what jackknife looks like. I fit my model on the training data. I fit every leave one out model on the training data. And then I take the 90th percentile of the leave one out residuals, and that tells me how big to make the margin of error around my predicted y hat, f hat of x, in order to have, hopefully, 90% coverage for, in terms of my predictive accuracy. So this is the jackknife method. And is it guaranteed to cover? So if I don't have algorithmic stability, we actually don't know. And it's not possible to prove completely assumption-free that it will cover. So one sort of silly reason is that it could be that f hat, which is run on n training samples, uses a completely different algorithm than f hat with one training sample removed, because for whatever reason, my code runs lasso if the sample size is even, and it runs a regression tree if the sample size is odd. And so the leave one out errors over here were run on an odd sample size and have no bearing on the accuracy of this model right here. So when we have something like that, like our silly counterexample is like doing something very different at sample size n versus n minus 1, that's a violation of stability. So if we instead assume stability, then you can have guarantees without any further assumption. So you don't need to know that like my model is consistent for the true regression, for the true mean of y given x. You don't need any distributional assumptions on p. So stability is enough to tell us that sort of things behave like they should. Okay, so this is all to say that basically stability is this fundamental property that we may want for downstream reasons for important statistical questions like generalization or predictive accuracy. And furthermore, we might want stability just for its own sake. Like, wouldn't it be weird if our algorithms were super unstable? It sort of feels like that can't really possibly be the right algorithm to use, whatever that means, if it's exhibiting huge instability. Okay, so what is the big picture? So one reason I think that stability is such a nice framework is that it's an assumption on the algorithm, which is in my control. Like, I can choose to use an algorithm that has good stability properties. I cannot choose to be analyzing real data that has smoothness or has linearity, because that choice is made by nature. So it's nice to be able to replace distributional assumptions with stability assumptions, because it's more under my control whether those hold or not. But when we really dig into that, it's a little bit more complicated than that, because we do not want statistical guarantees for methods that nobody's using. We want statistical guarantees for state-of-the-art methods. And if state-of-the-art methods are algorithms which are so complex that we can only think of them as a black box and we don't exactly know what they're doing, then can I really say, like, I don't know what's inside the black box, but I assume it's stable? Or are we worried about that for the same reason that we worry about placing assumptions on the distribution of our data? Like, how do we know if that's right? So at a high level, if we can't test whether our distribution that the data comes from satisfies, smoothness or something like that, we can try to use goodness of fit type things, but they don't always tell us when there's a problem. Then maybe we want to instead assume that the algorithm is stable, but then we ask ourselves, is that just replacing one untestable assumption with another untestable assumption? And if that's the case, then perhaps we need to think about, is stability helping us sufficiently, or do we need to do a little bit more? So what I'm going to be talking about is first understanding the extent to which stability actually is an untestable assumption. So that's the hardness result, and that's the bad news, that we are still placing an untestable assumption on our setup, on our ecosystem, which is the data distribution and algorithm as a pair. But the good news that we'll see in the second part of the talk is that actually something that's already very commonly being done, which is bagging, so some kind of ensembling of multiple runs of the algorithm, already induces stability, and so the assumption is going to hold. We don't need to worry about the fact that it's untestable. So that's the big picture of where we're going. Okay, so why do we worry about stability being testable or untestable? Because, of course, lots of algorithms are stable already. So something like nearest neighbors is already stable. That's just built in. We don't have to check it empirically. And the reason is that stability says, if I remove one training point at random, will my prediction change by a lot, or is that unusual? Well, if I remove a training point at random, it's probably not one of the nearest neighbors of the test point, because I just chose it randomly. And so as a result, my prediction actually would not move at all, unless, unluckily, I happened to remove one of the training points that is one of the nearest neighbors of the test point. So nearest neighbors is already stable. The same kind of thing also holds for ridge regression, or basically anything that places strongly convex regularization, as long as you place some additional assumptions on what it is you're regularizing. So if our algorithm is of this form, that I'm doing some kind of empirical risk minimization plus some kind of strongly convex regularizer, and things are Lipschitz where they need to be Lipschitz, then the strong convexity of the regularizer means that if you perturb the other part of the minimization, the empirical risk part, if you perturb it by removing one data point, the solution can't move too much, and then your prediction also cannot move too much. So these are some examples of algorithms that already exist. I didn't sort of construct some super convoluted thing in the interest of getting something stable. These are algorithms we already know and love, and they already are stable for free. But this isn't really enough, because, of course, this is not what's state-of-the-art for most applications. So why do we worry about stability? Let's see some examples where stability either fails or where we have no idea whether it's going to fail. So first of all, here's an example with least squares. And to me, this example is super compelling because what is simpler than least squares? And least squares already has instability. In this case, if you're near this transition at d equals n. So if your dimensionality is close to your sample size, least squares can be super unstable, basically because you're inverting a nearly square matrix, your X matrix, and it's ill-conditioned. And so this instability plot is showing, if it were exactly on the diagonal, that would show that the prediction for the with the full training set versus with 1 point removed are exactly equal. And the farther off the diagonal you are, the larger that perturbation is, like how much the prediction moved by just removing one training point at random. So you can see that least squares has the potential for instability. So this is exhibit A. Exhibit B. If we're using some kind of machine learning method that, that is, complex, sort of a real method that, not like one layer or something, it's too complex for us to theoretically analyze whether stability is going to hold. This is not something that we can try to understand other than empirically in many settings. And so really it's just a question of like, it's not that I see that it's unstable necessarily, it's that if I believe stability, that's because I'm placing an assumption. I don't necessarily know that to be true. Finally, this is just kind of a curiosity. I found out that if you go digging in R code for lots of popular packages, you can find these like if-then flags that are like, if the sample size is less than this, then do one thing, and if it's greater than or equal to this, then do another thing. So I have not seen empirically whether this gives you unstable results, but certainly it has the potential to. And this makes our silly examples of like, when n is odd, run least squares, and when n is even, do something else. It actually makes them a little less silly. We should worry about that a little bit. Because here are packages that literally say, if n is this, then do one thing, and if n is smaller, then do a different thing. And so if we happen to be near that sample size where that threshold is being set inside the code, but like we're thinking of it as a black box, so we didn't read the code, we don't necessarily know that the leave one out error might not be representative of the actual error of my fitted model because I have sort of crossed some kind of threshold in the sample size. So these are just some reasons for us to sort of wonder whether stability is something that we feel comfortable assuming or whether we should try to do a little bit more and verify it in a more principled way. Okay, so that's the background, and this tells us sort of why we need to ask, like, is it possible to test stability? So now I'm switching to part one. This is the work joint with Bjolken, asking to what extent can stability be tested, and as I've already given away the punchline, we're going to see that basically it's not something that's possible to do. So let me pause here first and ask if there's any questions. Okay. So before we go into our results, let me introduce what I mean by the black box setting. Because formalizing it was actually like bizarrely tricky. We were not sure how to write this down. So we intuitively know what we mean. We're treating the algorithm as a black box, meaning I run it, but I do not look at its code, right? So intuitively, that's just how we should think about it. And for our work, we are giving ourselves an unlimited budget in terms of how many times we can call the algorithm, because that's sort of being like as generous as possible to the problem, right? Like, is it possible to test if I don't have computational constraints? And of course, if I did have a computational budget, the problem would get even harder. So here are things that I am allowed to do. I'm allowed to run the algorithm on the real data. I'm allowed to subsample or bootstrap sample from the real data and run the algorithm again. I can perturb the real data or simulate from a model that I've fitted to the real data, and I can run the algorithm on whatever data sets I generate and sort of evaluate the predictions that come out. Here are things I am not allowed to do. I'm not allowed to calculate anything that implicitly is calling the algorithm like uncountably many times. So I'm not allowed to say, here's my data set. DL stands for like a labeled data, so it's XY data that I'm training on. Here's my data set, and I'm going to train on this data set and predict at some test point X. And now let me ask you this. What is the largest by which this prediction could move if I were to augment the training set with any other test point? I can't ask this question because I would have to calculate a supremum over all possible test points I could add to my training set, and I cannot do that in finitely many or even countably infinitely many calls to the algorithm. Now you might say, okay, well let me like just sample a ton of test points and try it many, many times. Yes, I am allowed to do that, but that doesn't necessarily estimate this supremum unless you assume that the algorithm is somehow continuous, and by sampling many, many possible points, you're kind of covering the whole space. So because we're trying to place no assumptions, I can do it for finitely many points, or count even like, let's say, countably infinitely many points, but I cannot search the entire like, Euclidean space, like RD that X lives in or whatever. I also am treating every fitted model as a black box, meaning that if I train my algorithm and I get a fitted model F hat, I can evaluate it on as many test points as I like. So I build a fine grid over the real line, and I look at what F hat it gives me at every point in the grid. But I cannot tell you definitively, for example, whether it's Lipschitz, because that would involve evaluating it at every point in the real line or RD or whatever space you're living in. So these are the things that you cannot do in the black box setting. So I'm going to formalize that in a minute. So what do we want to do? We want to construct a test that depends on the available data. So you have some amount of data labeled and additional unlabeled data that's available. That depends on the algorithm A only through calling the algorithm an unlimited number of times, but cannot look inside the black box. And I want to return a 1 or a 0, indicating that I do think it's stable or I'm not sure. It might be unstable. Now, what do we want it to do? So we want to play it safe. We do not want to say the algorithm is stable if actually it's unstable, because I want to know if my generalization doesn't hold, if my predictive inference isn't valid. So I want to bound error in this sense. You can kind of think of this as analogous to like false positives or type 1 error. This is the thing that I prioritize. For any algorithm that's not stable, so this is actually a triple, the algorithm, the data, the sample size, I want the probability of falsely declaring it to be stable to be bounded by alpha. On the other hand, this test is only useful if, when there's an algorithm that is stable, it's more than alpha likely to return a 1. Otherwise, it's not better than random. So I would like to say that for stable algorithms, or APN triples, the probability of returning a 1 is larger than alpha. Now, of course, it might be that there's some algorithms that are stable, but they're difficult for some reason. So this doesn't necessarily have to hold for like every stable A, but I'd like it to hold for like nice stable algorithms, or at least for some class of stable algorithms that the power is substantially better than random. So this is the goal. All right, so now let's back up and formally define what we mean by a black box test. And so this was like bizarrely tricky to try to write down. I still don't know if we exactly captured it, but this was our attempt. OK, so here's what we're going to do. Basically, we're just going to iterate the following. I call the algorithm, and then I strategize. I generate new data, I generate new test points, and then I call the algorithm again, and then I make some more decisions, and I go back and forth as many times as I want to. So at stage 1, all I have is my available data and unlabeled data. So XY pairs and additional X points drawn from the distribution. And I'm going to generate a new data set as any function I like of that original data. So for example, I could just take the original data. I could bootstrap from the original data. I could fit a parametric model to the original data and sample from it, whatever you want. Then I'm going to call the algorithm on my new synthetic or real or subsampled training set and fit this model. And then I'm going to evaluate this model on a bunch of X's and get the fitted Y's. OK, that's stage 1. And then I'm going to repeat. So at stage 2, I generate another data set as a function of everything I've seen before. So for example, let's say at stage 1, everything I saw indicated to me that when you have small values of X, as your test point, that's where instability happens. Then maybe at stage 2, I generate data that sort of is biased towards small values of X, so I can really like find that instability or something like that. So I generate some more data, I fit a model, I evaluate that model, and I keep going for as many times as I like. And finally, all of the output of all of those iterates feeds into whatever decision-making process I have, and that outputs for me a 1 or a 0, depending on whether I conclude that I'm confident it's stable or I'm not confident that it's stable. OK, so let's start with a baseline. What is like the simplest thing we can do? So let's say that my question is this algorithm stable at sample size 100? And let's say that I have 200 data points. The simplest thing I can do is to split those 200 into 2 batches of 100 data points, examine whether stability, like how big the perturbation is when I train on the first 100, how big it is when I train on the second 100. Now I have 2 independent draws of like how much things perturb when you remove one training point. And then I'm just going to compare that to epsilon and say, were those bigger than epsilon or smaller than epsilon? So generically, let me say that kappa is, Let me say that kappa is the number of batches of data that you can construct. So this is a non-integer, and then we're going to round it down to an integer. So if I have like 250 points, I can construct 2 batches of 100 data points that are independent from each other, and then I'm kind of like wasting the last 50. So these are batches of data of the correct size, sample size n, which are independent from each other. For each batch, I'm going to fit a model on the full data. I'm going to refit the model with 1 data point removed. I'm going to see whether the prediction moved. This delta k is how much it moved. I'm going to see whether the prediction moved by more than epsilon or less than epsilon, and for each k. And then I'm just going to compare that to the binomial distribution, asking, like, is the proportion of how many times it moved more than epsilon? Does that appear to be greater than delta? Or can I confidently conclude it's less than or equal to delta? So I'm just going to compare this empirical proportion against the binomial distribution and run a hypothesis test for literally just the parameter of a binomial distribution. And so that is my test t hat. And of course, we can check that this satisfies what we're requiring to be a black box test because it calls the algorithm 2 times kappa many times, but it never asks about the properties of the algorithm. It only uses the algorithm as a black box. OK, so here's our analysis of how well this test performs. So first of all, literally, I'm just doing a test of the binomial. So just by construction, it's going to be valid. What about its power? So if I have an algorithm that is stable, am I going to get substantially higher than alpha as my probability of declaring it to be stable? Because if not, then I'm not performing better than random. So it turns out that this depends on a number of things. So first of all, we have to look at this delta star e, which is the value of delta for which stability holds. So if the question I'm asking is it epsilon delta stable, where delta is 0.1? So I'm asking, is it true that large perturbations happen no more than 10% of the time? And the truth is that, yes, it is stable. And the reason is that the probability of the large perturbation is less than 10%. It's 9.99999%. I'm not going to be able to detect that unless I have an enormous amount of data. So that's where this ratio comes from. If I'm asking whether the perturbation happens at most 10% of the time, I'm only going to be able to detect that if actually the perturbation happens substantially less than 10% of the time. So that's where this ratio is coming from. And then to the power kappa is because I have kappa many independent draws, like that gives me my binomial with kappa as my number of flips of the coin. And so the more times you flip a coin, the more power you have to detect that that coin has a low probability. So the most important thing to notice here is no matter how stable it is, like even if delta star is 0, so it never moves by more than epsilon when you perturb it. Even if delta star is 0, this ratio is 1 over 1 minus delta, best case scenario. You usually want a small delta, right? Like you don't want something that's like, yay, it's stable because the perturbation is large only 50% of the time. No, I want delta to be like 0.1, 0.05, something smaller. So this ratio is barely bigger than 1. If I want my power to be substantially better than random, I'm going to need to raise this to an enormous power. I need kappa to be huge. So what this tells us is that if I'm asking, are you stable at sample size 100, I cannot answer that with high power with this test if the available data I have is 200 data points. But if the available data I have is 10,000 data points, then I'm in great shape. So which regime are we interested in? And the answer is bad news. We're interested in the regime where kappa equals 1. Because if I have 200 data points available, for example, I don't want to tell you that if you lived in a universe where you only had 10 data points available, then your fitted model would be really stable. I want to tell you that your fitted model is going to be stable when you run it at the sample size that you have. So really, for practical purposes, I'm interested in kappa equals 1. And this tells us that the power is low. Now, maybe we're not surprised. This test is so naive, right? Like, we barely make use of the data. If you have 200 data points and you split it into 2 batches of size 100, shouldn't we resample that like 1,000 times and get a much more accurate answer? So this is where the hardness result kicks in. The binomial test seems to not make efficient use of the data. Like, we never bootstrap. We never reshuffle how we split the data into batches. But it turns out that the binomial test is actually optimal. So like the most naive and low power thing cannot actually be beaten. So this is our result. which is that if you have any black box test of stability that's universally valid, meaning that for every algorithm, for every data distribution, it has to not have a higher than alpha error rate at falsely declaring stability, then the power of that test is upper bounded by the same exact expression that we saw for the binomial. So with one caveat, which is that here it's kappa without rounding down. So if I have like 2.5 batches of data, I get higher power here than I did for the binomial. But if kappa is an integer, you get the exact same value. A second caveat is that for the binomial distribution, the power calculation was in certain regimes of delta and alpha. But when delta and alpha are both fairly small, which is the regime of interest, we want small error rates, the powers match exactly, up to just rounding kappa to an integer. OK, now I want to point out that what this result is saying. This result is not saying there are some algorithms for which you have low power. This result is saying for every single triple, for every A, every P, and every sample size, no matter how stable it is, your power is not much better than random. So there is not a single algorithm, no matter how nice it is, that gets high power. And the reason is that even the nicest algorithm in the world is still extremely close to a really horrible algorithm that's like the counterexample that proves this bound. So this is saying that it's like uniformly powerless. There are no algorithms that are certifiably stable if you want your certificate to be universally valid with no assumptions on A or on P. OK, so when we worked on this, the reason this project started is because we were trying to construct a test of stability. So this was like kind of a shock and a disappointment that like it turns out like you just cannot do it. And so we're going to see in the second half of this talk that we can avoid the need for this by using a wrapper around our algorithm, by bagging our algorithm so that it becomes stable theoretically and we don't have to validate it empirically. But what this tells us is that basically validating stability empirically is not possible to do assumption-free. Every test that is a black box test and is universally valid has low power in the regime of interest, where you have a sample size that is the same sample size as the question you're asking. So I have 1,000 data points. I'd like to know whether the algorithm is stable when trained on 1,000 data points. OK, in particular, this tells us something really counterintuitive. Simulating doesn't help. Modeling doesn't help. Bootstrapping doesn't help. None of that adds information because it cannot increase the power. So why does that contradict our intuition so much? It's because when we simulate or bootstrap or whatever, we are saying, I am creating data sets that are very close to the behavior of the real data. And so the algorithm's performance should be very similar to the performance of the algorithm on real data. When we think like that, we are placing a continuity assumption on the algorithm, that when I feed it similar data, I get similar behavior. The reason that this doesn't work is because if your algorithm is arbitrarily non-smooth, creating copies of your data that are very similar to real data gives you no information because we're not assuming that the algorithm behaves in a smooth way and would behave similarly on realistic but not entirely real data. OK, let me give a quick proof sketch before we move on to the second part. So basically, the idea is like standard in these hardness result type constructions. I'm trying to distinguish between stability and instability. And what I need to show you is that for anything that's stable, there's something super close to it that's not stable. And I cannot tell them apart. So that's the idea. So what we're going to do is that given any stable triple, we're going to construct a triple where I slightly change the algorithm and I slightly change the distribution, but very, very slightly. So first of all, the two distributions are going to be so similar that drawing data from P and drawing data from P prime, even at the sample size you have, so like drawing 1,000 times from P, then drawing 1,000 times for P prime, their total variation distance of that entire sample is very small, so I cannot really tell them apart. And I'm also going to construct the perturbed algorithm A prime so that if it observes data that was drawn from the real P, it will 100% of the time give you the exact same fitted model that the A algorithm would have given you. The way we do this is by saying, I'm going to create a P prime that has a small probability off of the support of P. And if the algorithm A prime sees something on that sort of area where real data never occurs, then it's allowed to give you a fitted model that's terrible. But if it only sees data from the support where real data might occur, then it's going to just run least squares or whatever A is doing. And so with these constraints in the first two bullet points, the probability of returning an answer of 1 is approximately the same, whether your data and fitted models are coming from AP or A prime P prime. Now, if A prime P prime is constructed to not be stable, then the probability of getting a positive answer, of saying, yes, it's stable, has to be bounded by alpha by validity. That's the definition of what a valid test is. So as a result, the probability of getting a positive answer for the thing that actually is stable is approximately bounded by alpha. So what do these constructions look like? So the upper bound on power has two parts. First of all, there's the bound that comes from a limited amount of labeled data. So if my sample size of interest is 100 and I have 200 labeled points, this exponent is 2. I have 2 batches of training data that are independent from each other. So the distribution P prime is going to almost always sample the same xy as P does, but occasionally it's going to give you a response value where it like removes the actual value of y and sort of plants this artificial value of y that had a 0 probability of occurring under the real distribution. So in other words, if you see it, you know this data was perturbed. You know it was corrupted. Then the algorithm is going to say, if the sample size is equal to n and you observe this planted corruption anywhere in your data set, then return a prediction that's corrupted. If not, then just return the prediction that would have come from least squares or whatever the algorithm A is. And we're going to pick these pink things, the fraction of corruptions and how the corrupted prediction is constructed, such that the counterexample is not stable, but it's really, really close to the real algorithm A and the real distribution P, which are stable. Now, the second part of the bound is that we also have a limited total amount of data. So the total number of x values that I see is given by the number of labeled points plus the number of unlabeled points. So for this second construction, we do the same thing, except instead of planting a corrupted value of y, we plant a corrupted value of x. Again, something that has 0 probability of occurring under the true data distribution. And then we do the same thing where if you see that corrupted value anywhere in your data set, you return a corrupted prediction. Otherwise, you return the original prediction from the algorithm A. So this is what the construction looks like. And again, moral of the story, all that it's telling us is that when you make no assumptions at all, any algorithm that is stable is indistinguishably close to something that is not stable. Okay, so to summarize part 1, what have we seen? We've seen a simple binomial test that's like a complete naive baseline for black box tests of stability, but we've also seen that we can't actually improve on it. And again, this is because bootstrapping or anything else is only useful if you believe your algorithm is continuous or something like continuous, so that creating similar data to real data gives you similar behavior to the behavior on real data. When we don't make those assumptions, we are unable to do anything more powerful than the binomial test. So what are the open questions we're left with right now? So first of all, we don't believe that algorithms are arbitrarily bad. Like maybe they're super complex, but they still are doing something sensible. So what are some mild assumptions that would make stability testable? So I have no idea, but I think this is a really important question to try to understand what are like the mildest assumptions that would make this issue go away. We can also ask, instead of assumptions, maybe it's the goal that's the wrong goal. Are we using a definition of stability that's too strong? And there would be some weaker definition of stability that is testable, but is still sufficient for downstream implications like generalization. And then finally, leading into the second part, if we can't test stability, can we instead ensure stability by doing something differently? So I don't want to throw out my state-of-the-art algorithm and instead use least squares with ridge. I instead would like to benefit from the accuracy of the state-of-the-art algorithm, but just sort of safeguard it in some way so that if it happens to be unstable, we've removed that instability. Okay, so this leads us into part 2. Let me pause again and ask if anyone has any questions. Yeah. Yeah, that's a great question. Okay, so I don't know if sequential is the only way to define black box, but let me try to explain why black box is necessary, and maybe that's sort of next door to the question you're asking. So we need this to hold. We need to say that if I were to run my test on AP, that gives me this similar probability of returning a positive answer as if I were to run it on A prime P prime. So it has to be black box because if the first thing my test does is open the code and check whether it's least squares or whether it's something weird that I did to least squares, it could immediately see the difference, right? So I need it to be black box. Okay, so how do we prove that this holds? So what I need to prove is that at stage 0, where like nature hands you some available data, P and P prime are close together in total variation distance, even when you sample 1,000 points from each. So there's a small probability that nature will hand you data that has the corruption in it and like visibly is not data real data, and that's the difference here. That's when these are not equal. But with large probability, like 1 minus this TV distance, nature hands you data that's entirely from the real data distribution and 0 corrupted points. Okay, so if that's the case, then if all I were to do is just look at that data and fit the model just on that data and compare them, they would be the same from AP as from A prime P prime. But the thing is that I actually move on. What I do is I take that data, then I bootstrap from it, then I model it, then I simulate from it. And when I'm running these two parallel processes, AP versus A prime P prime, the original data is exactly the same with a high probability because of this first statement. But the question is, as I go through my sequential list, do A and A prime always give the same answer? Or at some point, do they diverge because the corruption wasn't in the original data, but it was at stage 11 or something like that? A prime detects the corruption, gives you a different model, and I can declare stability for A, but instability for A prime. So what we actually have to do, what we actually have to do is we have to pick this y point slash this x point. We have to pick the corruption point in a slightly more complicated way than what I said out loud. It's something that has 0 probability of arising in the real data and has 0 probability in arising from any bootstrap or simulation or anything that I'm going to run on top of the real data. So basically, like, if the real data is on the integer grid, but then what I do is I fit a Gaussian to it and I sample from that Gaussian, I need a point x star slash y star that has 0 probability of arising at either the real data stage or my simulation stage. Now, if we pick it so that it has that 0 probability, then what happens is in this definition, like inductively, at every single stage, I have a 0 probability of seeing the corruption if my original data didn't contain the corruption. And so then by induction, the outputs of the real AP test and the imaginary A prime P prime test are the same all the way through. So that's kind of where the sequential structure comes in and where the black box assumption comes in. I'm sorry if that didn't answer your question, and I'm sorry that was so long, but hopefully that clarified what you were asking.
I think it makes sense why it needs to be countable in some sense because of this, right?
Yes. Yeah, because like basically you just need something that has 0 probability of ever being seen. And so because countable probability is sum, you can just say like, I just need something that has 0 probability of being seen at each stage.
I have a follow-up question that is, feel free to say no, and that's the end of it. Does this relate at all to you, to the hardness of the conditional independence testing? Does the construction or the flavor of the result?
Okay. Not in any way that's transparent to me right now, but yeah, I think the constructions feel at least fairly different to me. Yeah, that's a good question. I'm not sure if there's any like obvious similarity there. I'll think about that. Other questions? Okay, moving on to part 2. This ends at 10 past, is that right?
Yeah.
10. Okay. All right. So, so the question we were left with at the end is, if we can't test stability, can we at least make things stable so that we like avoid the need to test stability? And at a high level, here's the goal we want. I don't want to throw out my algorithm and instead run nearest neighbors for like everything, right? What I want is some kind of post-processing step that makes any unstable algorithm stable. But if your algorithm was already stable, I want it to not change at all, right? Like I want to keep the good performance of whatever state-of-the-art algorithm you were using. Now that's not possible exactly, but at least I can say for any algorithm that's stable, I don't want to change its performance too much. If it's unstable, I'm happy to modify it. It has to change because I need to make it stable. And empirically, bagging and other ensembling procedures have been used for a number of reasons for years and years, partly because they've been observed to introduce stability, also because they can improve accuracy and all sorts of other favorable properties. So here's what I'm thinking of as sort of a generic construction for like the basic version of bagging. I'm going to take my data set of size n, my training data set. I'm going to sample a bunch of subsets and fit models to each of those subsets. And at the end, I'm going to aggregate. And in this talk, I'm thinking of just averaging to aggregate. Of course, you could have other choices that may be better for certain applications. But here, we're just studying the mean as the aggregation procedure. So the two most common methods for this are what I'm going to call classical bagging, to distinguish it from the term bagging more generally to mean like any kind of bagging. So classical bagging is something like bootstrap, where you sample n times with replacement from your sample of size n. But more generally, you can sample m times with replacement from your sample of size n, where m could be different from n. You can also do what's known as sub-bagging, where you sample without replacement. Here, the most common choice would be something like m equals n over 2. So take a random half of your data, train, repeat. All right. In both of these options, I'm going to be using p to denote what fraction of bags contain any single data point. So here it's just m over n, and here it's the here it comes from looking at sampling probability calculations from sampling with replacement. Okay. So bagging appears in lots of places, so it comes up in random forests. It's used for what's called stability selection in the variable selection problem in regression, and tons of other places. And again, this is something that's already being used super broadly and empirically has been observed to create stability in lots of settings. But understanding that theoretically has been restricted to certain specialized cases. And what we're interested in is just more generally, why does bagging seem to bring stability? So there's lots of results on theoretical properties aside from stability. Bagging reduces variance. It creates more smoothness in your output. It's more robust. And there's some results showing stability of bagging for generic input algorithms rather than like specifically for random forests or something like that. In limited regimes, specifically where you're massively subsampling, here we're going to consider a general case where the subsampling might be order n. So bootstrap, you sample with replacement n times, which is probably more common to use in practice unless the sample size n is enormous. All right, so here's some empirical evidence that bagging really does help massively with stability. So here's 3 base algorithms. Logistic regression in an unstable regime, which for logistic regression is when the dimension is around half the sample size, a neural network, and regression trees. The red histogram is how much does the prediction jump when you remove one training point at random. And the blue histogram is same question, but instead of asking that question for logistic regression, I'm asking that question for bagged logistic regression. So my algorithm is the thing you get when you run bagging on top of logistic regression. So for all 3 of these, we see that instability is pretty bad in red for the base algorithm. It's much better in blue for the bagged version of the algorithm. Okay. So let's ask again what we're asking about for stability. And here the definition is actually going to change a little bit. So in part 1, we said that an algorithm is stable relative to a particular distribution. That when I sample my data set, IID from P, and I test on a test feature vector X also drawn from P, then when I remove a data point at random, my perturbation is usually small. We're going to ask for a stronger definition now because it turns out this is more natural for this problem. I'm going to train on an arbitrary data set, test on an arbitrary test point, but I'm still going to ask about removing one training point at random. So when I randomly choose a training point to pull out, that's my average over I. Is it the case that the perturbation is small for most I that I might remove? Maybe there's a few training points that are like super influential and they jump by more than epsilon when they get removed. So here's our main result. Sorry, I think I might have a typo here, but anyway, P is the probability of a data point being in a particular bag. So we often have P being a constant somewhere between 0 and 1, like for example for bootstrap, or for sub-bagging with m equals n over 2. What this tells us is that for absolutely any base algorithm, if the predictions it outputs lie in a bounded space, then as you take the number of bags to infinity, stability is automatically satisfied with no assumptions on the data set, on the test point, or on the algorithm aside from boundedness. for any epsilon and delta that are larger than this threshold. So we'll see in a second kind of like how that plays out, what that means. But basically this is saying that like at a certain level, stability is free with bagging for any algorithm that you plug in. So we'll look at some concrete regimes in a second. I just want to mention that I'm stating the sort of cleanest version, but you can easily extend this to allow for randomized algorithms, to use a finite number of bags, because of course that's what happens in practice, or to even to have models with unbounded output. You can have like a slightly more complicated version of this result by rescaling to consider not the bounded range of predictions, but the actual empirical range of predictions. So I'm not going to state them here just for the sake of having a clean result, but the result does build out to those extensions as well. Okay, so what does this mean? Let's look at 3 regimes. So first, maybe most commonly, or at least what I'm most familiar with, is the proportional sampling regime, where each individual data point on average appears in a constant fraction of bags. In this case, stability is guaranteed when delta epsilon squared is on the order of 1 over n. So this is great. It means, for example, that if you take each of them to be n to the minus 1/3, that means that at most n to the minus 1/3 fraction of training points are influential enough for the prediction to move by more than n to the minus 1/3. So this is telling us that stability is happening with like vanishing probabilities of failure, vanishing bounds on the size of the perturbation. You can also think about massive subsampling, and this is a regime that was previously studied in the literature. Here you might say something like n is enormous, I have an absolutely massive data set, I can't even train on a sample of size n. Let me take random samples of size root n, train on those, and aggregate. In this case, because you're subsampling more, stability is easier to achieve, the scaling is stronger. Now, what's really interesting to us is that you can actually also go to this third regime that we think of as minimal subsampling. I'm going to train on the entire data set of size n with only, for example, root n many points removed. So I think of that as sort of barely perturbing the output, and you're not losing any quality in terms of like your, say, parametric rate for like how well the algorithm is being fitted, because I am only removing a vanishing fraction of my sample size. But we still get a stability guarantee just at like a slower scaling. So this last one is, to me, what's really compelling when we think about what we want. We want something that makes unstable things stable, but if you're already stable, we don't want to ruin a good thing. We want to give output that's very similar to the output of the original algorithm, which was already performing well. And so what this tells us is that if you're already stable and I remove a vanishing fraction of points, I'm probably just giving you very similar output. So we're sort of costing, it costs very little to do this kind of bagging when you're doing minimal subsampling in terms of the performance and the accuracy. Okay, so as a quick proof sketch, this is actually just like a counting argument or a double counting argument. So I know I'm running out of time, so I won't go into this in detail. But basically what we're going to look at is we're going to say what points have large perturbations, perturbations greater than epsilon. Let me look at the sum of those perturbations. If I index that over counting i's, so counting which points are bad, which points give you a large perturbation, you can see that this sum is at least epsilon times the number of bad points, because epsilon is how big the perturbation is for each bad point. But on the other hand, double counting, I can alternatively rewrite this as a sum over bags. And when you rewrite it as a sum over bags, then you get a clean expression over here that basically tells you that we need to just do a variance calculation over like how many bad points are contained inside the bag effectively, and that gives us our upper bound. So I'll just skip ahead in the interest of time. All right, so let's quickly see some empirical results. So I'm going to show you the same 3 base algorithms: neural nets, random regression trees, and logistic regression. What we're going to see for all of them has the same format. This dotted line is the stability guarantee that we get theoretically. It tells us that for delta epsilon that's on the line or above, any algorithm will be that stable for if you bag it. Below it is stronger stability. If I have a point over here, that means that's an algorithm that's epsilon delta stable for a smaller epsilon and a smaller delta. So now what do we see? We see that this neural net was more unstable before bagging, but after bagging, it got more stable. The curve shifted down and to the left. And in particular, it matches our theoretical guarantee because it is at least as low as the dotted line. So it is more stable than what's guaranteed by the theory. Basically the same picture for regression trees. These were actually highly unstable before bagging. And then finally, this is the really interesting one. This is logistic regression. If you run logistic regression where the dimension is around n/2, it's highly unstable. And that's because you're near the phase transition where like the data can be perfectly separated with a linear function into the positive and negative labels just by random chance. That makes it highly unstable. If you run it with d = n/4, it was already stable and it didn't even need to be bagged. When we add bagging on top of this method, it's stable either way. And so we made something unstable more stable. If it was already stable, then the behavior didn't change very much, which is what we want to see. Now, finally, what we can see is that this guarantee is tight. We can construct an example explicitly that matches the same thing up to a constant, meaning that it's not possible to prove a faster stability rate universally over all algorithms. And just visually, you can see that there's a constant gap, but not too bad, between the stability that we prove in blue versus the counterexample we can construct that like gets pretty close to the guaranteed stability threshold. So there's a little bit of a gap, but it's only a constant. So it tells us that this is the equation that characterizes how much stability does bagging introduce for the worst case algorithm. All right. I know I'm out of time, so I'll skip the proof sketch for the tightness bound. And let me just say that we consider average stability, which is you remove a training point at random. If we had instead considered worst case stability, like no single data point, removing like an adversarially chosen data point, still cannot perturb too much, that's actually a really strong assumption. You're like not allowing for influential data points. And so in that case, you can get stability if you have a really small p. So like I'm subsampling 1% of my data. That means that most points cannot be influential because they're not in nearly any of the bags. But you cannot get a stronger stability guarantee. So if you want bagging to universally guarantee stability, we have to define stability in the sense of removing a training point at random. We cannot hope for this stronger type of result. Okay, so to wrap up, what we see is that bagging can be applied to any algorithm and give stability. And that means that we don't need to know anything about the algorithm. We can just say, if I put bagging on top of it, I am ensuring that this untestable assumption is guaranteed to hold. And of course, bagging hopefully improves accuracy or at least doesn't ruin it too much. And so we are getting increased stability without compromising on state-of-the-art performance. We still have tons of open questions. We can ask about other definitions of stability. We've really only considered one. We can look at aggregation procedures aside from averaging, or we can even ask whether there's things you can do other than bagging that get you to the same place. And finally, not all predictions and outputs are real valued. So it's an interesting question to ask, like, how does this work if what you're outputting lives in a completely different space, which is also something where we want stability. Okay, so with that, let me thank you all for coming, and I look forward to your feedback.
Okay, if you want to ask a question, let me bring you the microphone.
Thanks for the great talk. So I have a question about this second part. I guess if our goal downstream is to prove some kind of generalization, often we will assume stability that's like in terms of perturbing the loss if I like remove or replace one training point. So I'm wondering if there's like a reinterpretation or maybe adaptation of the results of the second part where I could get stability in this loss sense.
Yeah, that's a great question. So a lot of these results are like how hard it is to get whatever, may actually be a lot easier if you think about only stability for the loss. And the reason is that if your loss as a function of f is Lipschitz, then as soon as you have a guarantee on the perturbation of f, you have a guarantee on the perturbation of the loss. But it's very possible that by using knowledge of what the loss is, we might be able to prove things about stability on the loss that we like cannot prove about stability of f. So I think there's potentially like a large asymmetry there. I don't know. But in any case, if you do have this guarantee for f, you automatically have it for the loss. So assuming it's Lipschitz. So the second part applies. Whether the hardness result applies for stability of the loss, that I have no idea because it sort of like goes one way but not the other way. So maybe the impossibility result doesn't extend there. That I don't know.
Yeah, I was thinking more like if there's some counterpart of bagging that we can directly think about in the loss space, and if there's maybe like a more direct correspondence between also the lower bound and the upper bound in the loss space. But maybe that's a question for...
That's a great question. So let me clarify what you mean. Do you mean that we would do bagging on the function itself, but then directly try to prove something in loss space? Or do you mean that somehow we're actually aggregating losses?
Sometimes we're
functions?
aggregating losses.
Ah, I have not thought about that. That's a really good question. I don't know in what settings you need, like it might be the case that in some settings you need to aggregate functions in the sense that the thing I hand you at the end has to be a function. But for other results, it might be okay to aggregate losses because there's some other downstream goal. So that's a super interesting question. I don't know how to study these different regimes.
Thank you.
Anybody else?
Thanks for the great talk. I have two small questions. The first is about the part 2. Like, do you require the number of bags is approaching infinity to achieve the result?
Both yes and no. So to get this exact result, yes, this is at b equals infinity. If you want to use a finite b, you basically have Hufting's inequality. Okay, it's very possible that there's a more sophisticated way to do it, but we just did the simple thing and used Hufting's inequality. So basically what's happening is that what you do with infinitely many bags, you do it on f hat, and you also do it on f hat with one data point removed. Now, the actual f hat and f hat minus I that I fit with b many bags are converging to the ones I would have fitted had I averaged over infinitely many bags, because we can think of the bags as like IID draws from the population of all bags. So Hufting's inequality tells you that f hat converges to the like f hat with infinite b, and f hat minus I also converges to f hat minus I with infinite b. And then this result tells you that those two infinite b functions are close together. So effectively, you just have a triangle inequality. It's like nothing sophisticated. But Hufting's inequality tells you that basically as soon as b is large, then you get sort of a, something along these lines. But it's just more messy because it has like 1 over root b terms in it.
Okay, that's helpful. And another question is about part 1, the definition of stability is about like missing one data. Like, is there other notion of definition that like if you miss more data, will the result change or like?
Yeah, that is a fantastic question. So this is actually something that my group has thought about a very little bit in a different context, which is that we're working on something where it seems like stability should be the right assumption, but it seems to not quite be enough. And so we're looking at exactly what you're proposing, like what about stability to a small fraction being taken out rather than one being taken out? How that would play out in terms of these results of like, does bagging give you that stronger form of stability in sort of an elegant way? I think that would be really great to consider. We've not looked at it at all. So yeah, that's a great question.
Yeah, thank you.
Okay, I think we have to finish up at this point. Well, Ryan, I can't not. Ryan to finish up for us.
Well, now there's a lot of pressure. So this is actually more of a comment / question, but are you aware of the connections between bagging and ridge? Have you seen these things before?
Between bagging and ridge?
Yeah.
I don't think so. I would love to see that.
Okay, so
Very
there are some recent papers that show that bagging and ridge have equivalent asymptotics. So for things like
Wow.
least squares and kernel regression, for example, they are the same in certain regimes. And those results are actually pretty general. So they don't assume much about the data either. So it's kind of a neat connection because bagging is, in instances in which you have a loss function, I think you can think of bagging as acting like ridge.
Oh, that's fascinating because basically like we already know ridge has finite sample stability and here we see that for bagging, and then this is kind of, it sounds like what you're saying is this is an asymptotic explanation that the two are stable for the same reason.
Yeah.
Yeah, that's very cool. I'd love to see that.
Just to bring up Leo Bryman's name. So Leo was here when I came, and he in fact helped bring me here. Leo invented bagging, and it was fun to hear bootstrap aggregating, and it was fun to hear him talk about it. I'm sure he would have been very, very proud and happy to hear Rina talking about all these things.
Oh, thanks
all right,
so much.
So,
yeah, it's great to be here.
Thank you, Rina. It was